Okay, so this one's divided up into two parts. We're talking about how planes can intersect. And firstly, we're going to talk about the intersection of two planes in space. And so if we're on page 53 of our notes there, we've got all of the ways in which two planes could intersect. Remember, planes, like lines, go in every direction forever. They're going in that direction forever. So we could have planes, two planes, they could intersect along a line. They could be parallel, in which case they never meet, and they could be coincident, in which case they are the same plane. Now, what I've got alongside on the right-hand side of this table here, this shows you what the matrix will look like once you have reduced it, and which one corresponds with which geometric representation. So for example, if we obtain this row echelon form, once we've reduced it, then we know the planes intersect. If we obtain this, where we have 0, 0, 0 in the bottom row and then a number, G, we know that they're parallel. And if they're coincident, then we have all zeros in the bottom row. So let's solve the first one. In the first one here, we've got some numbers. And then in the second one, we've got a value of K that we're going to solve for two solutions. Okay, so we've got, here's the system of equations, two equations, and I've presented it in row echelon form. Let's reduce it. Okay, so we're going to reduce this matrix. We have 2, 1, minus 1, and 5 at the top. And I have 2, what am I going to do? I'm going to replace row 2 with with row 1 plus 2 lots of row 2. Okay, I'm going, that's positive, that's negative. So now if I add them together, I'm going to have 2 plus negative 2, that's going to give me 0 here. I'm going to have 1 plus 4, give me 5, and minus 1 plus 8 will give me 7, and 5 plus 14 will give me 19. Okay, so we've performed a row operation, and now we're looking alongside at the echelon form, and we're going, which one does it match? And it matches the top one. Okay, we have a 0 here, and we've got these two numbers equal to 19. And so this means we have two intersecting planes, and they intersect. If two planes intersect, they're going to intersect along a line, and we can solve that line by using the methods that we just learned. Okay, we're going to let z equal t. Then we have 5y plus 7z, 5y plus 7t equals 19. We can solve here for y. And then we can solve through for x. We'll have 2 lots of x is equal to 5. Take y plus z. And minus 19 on 5. Positive 7 on 5 plus 5 on 5 is 12 on 5. Our solution, sorry, that's 2 lots of x, and then divide by 2, just gives us 10. Okay, so that's the equation of the line. It's a line presented in parametric form, right? Here's the x value, here's the y value, here's the z value. And you can find any point along that line. Okay, good. Now we've got, consider these two planes, determine the value of k for which they're parallel and for which they're coincident. So the first thing we're going to do is try and reduce this matrix, all right? So I'm going to replace row 2 with 2 lots of row 1, take away row 2. So the top row stays the same. Now 2 times 3 is 6, 6 take away 6 is 0. 2 times 2 is 2, take away 2 is 0. Minus 4, take away minus 4 is 0. And then we have 10, take away 2 lots of k, 20. 20, take away 2 lots of k. Okay, so this is a really easy question for us to answer. It says, determine the value of k for which the planes are parallel and for which they're coincident. Okay, so they're going to be parallel provided this is a number. Okay? It can't be 0. All right, they're going to be coincident. We're looking at our echelon form. They're going to be coincident when this is 0. So we can write that up. It's coincident when 20 take 2k equals 0, and we can solve that, right? We'll have, yeah, minus 2k minus 20, k is 10. Okay, so they're coincident when we have a 0 here, and we're going to have a 0 when k is 10. And they're going to be parallel when we do not have a 0 here. That means that 20 take 2k does not equal 0. And we can solve accordingly.
The k doesn't have a 2 as its coefficient.
Oh, sorry. All right, 20 take k minus k, k is 20. There we go. Fortunately, it's an easy fix. And so then, provided k does not equal 20, we will have parallel planes. Okay, is that clear? So if k is 20, we're going to have a 0 in this position, which means we're going to satisfy the third manner in which two planes can be orientated. And if k does not equal 20, we're going to have some number there. We're going to have some constant there, which means it's the second one, that the planes are parallel and they're never going to meet. Very good. Let's flick over the page. Now, question 3 here is again about two planes intersecting. And we won't go through this whole one. I'm just going to talk about how you would solve each part so that we can get onto 3 planes intersecting. So it says, consider the planes P1 and P2. We've got the equation there. Show that point A lies on both planes. Now, how would we show that a point lies on a plane? It's the same way we would show that a point lies on the line. If a point lies on a line, then it satisfies the equation. If a point lies on the plane, then it satisfies the equation. So we're going to substitute the coordinates of A into the equation of plane 1, and we'll see that the left-hand side equals the right-hand side. We'll substitute the coordinates of A into plane 2, and we'll see that it also satisfies plane 2. And so thus we'll know that the coordinates of A lie on both plane 1 and plane 2. Okay, part B says, find the equation of the line of intersection. Okay, these are going to intersect. How? Well, we're going to state them in the matrix and then reduce them and then find the equation of the line using the strategy that we've presented here. That's how we find the equation of intercept. Find the angle between the two planes. That's an exercise we just did in 6J, right? And then we've got some other things in there that involve finding the distance around it and so forth. So that's a bit of extra problem solving for you to have a bit of a crack at. Involves a bit of Pythagoras theorem and so forth. Okay, so let's talk about 3 planes and how 3 planes could interact then. And so we've got, if we have 3 planes in space, I'm on page 55 now, we've got 8 possible arrangements of the ways in which they could interact with one another. So we could have that all 3 planes are coincident, they all describe the same equation. We could have 2 are coincident and one intersects the other. We could have 2 are coincident and one is parallel, so it's like hovering above it and the third plane never meets. We could have 2 parallel and we could have 1 plane intersecting both of them. We could have all 3 being parallel, and if all 3 are parallel, that means there's going to be no solutions. They never intersect at all. We could have all 3 of them meeting at a single point. All right, so that's the 6th orientation. The 7th orientation, we have all 3 meeting along a common line. And then the 8th orientation, they're sort of 2 planes that intersect, every 2 planes are intersecting, but there's no common intersection with all of them. Okay, now we can use our understanding of row echelon form and our understanding of parallelity, or if planes are parallel and if planes are coincident, to determine which geometric arrangement is occurring. So let's flip the page, and I've got for you here 8 to work through. We'll go through a few together and I'll just explain how we know which configuration is occurring. So for the examples here, we're going to be flipping back and forth between the 2. So the first one we've got written there says all of the planes are coincident. How can we state that that is true? How can we show that that is true? The system of equations that we have is x, take y, take 2z is 1, 2x, take 2y, take 4z is 2, and minus 4x plus 4y plus 8z is minus 4. So what we can do is we can just say, well, row 1 is equal to 2 lots of row 2, which is equal to minus 4 lots of row 3. And so what that demonstrates is all of the planes are scalar multiples of one another. We can see that. If I multiply this row by 2, I get this one. If I multiply row 1 by minus 4, I get this one. So all of the rows are scalar multiples of one another, which means all of the planes are the same. They bear the same relationship. Therefore, all planes are coincident. Okay, if we can demonstrate that planes are scalar multiples of one another, then they are coincident. Okay, in number 2, we've got 2 are coincident and one of them is intersecting. So how can we demonstrate this is true? So I'll write it up here in row echelon form. 2 and 1 minus 2, 1, 4, 2 minus 4, 2, 8. Okay, so we've got 2 of them are coincident and 1 of them is intersecting. Now, if we're looking at it, we're going, okay, 2 of them are coincident. Can I see some scalar multiples here and between row 2 and row 3, okay? Row 2 is double row 3. So that means if we're to do row operations to break it down, all right, what we would have is we would have 2 lots of row 2 take away row 3, let's do it. 2 lots of row 2 take away row 3. And then what are we going to be left with? 0, 0, 0, 0. Okay, now we've already done an example like this where we can break it down further. We can get a 0 there, we can go let z equals t, and then solve the equation of a line. Okay, so we can find, if we're just looking at this matrix, we can establish that there's a solution that lies on a line. However, there are lots of solutions that lie on the line. Let's flick back the page and let's explain what's going on with the table at the bottom. So we've got 1, 2, and 7 have infinitely many solutions. And if you think of a line, they meet in a line, well, there are infinitely many solutions that lie along the line. That's what's going on there. And if we do reduce it down, okay, if we reduce this further, we will have a 0 here, which means they do meet along the line. However, then we go, all right, well, that means it's either arrangement 1, 2, or 7. How can we establish which one it is? Well, we know it's not 1 because 1 requires all of the planes to be coincident. We only have 2 planes that are coincident. Okay? How can we establish that it's not number 7? Well, number 7 doesn't have any planes that are coincident. Okay? Number 7, all of the planes are different. So this is like a deductive process of elimination. It's not 1, it's not 7, therefore the arrangement has to be 2. Where we have 2 planes are coincident and the third one intersecting. Okay, moving on. Any questions so far? All right, for the arrangement. We've got, how about if we have 2 that are coincident and 1 that is parallel? Okay, if we have 2 that are coincident and 1 that is parallel. Okay, so let's just look at them. We can see plane 1 or row 1 and row 2 are scalar multiples of one another. So they're parallel, right? And so that means when we go, you know, if we replace row 2 with 3 lots of row 1 take row 2, we'll have all zeros in row 2, which means we can go on to find the equation of a line. We can also, however, see, I might have to do this one actually, rather than just talk about it. Okay, so we've got 1, 2, 3, 1, 3, 6, 9, 3, minus 2, minus 4, minus 6, 2. Okay, good. All right. So if we try break this down, all right, maybe what we can see is all of the directions are scalar multiples, let's break it down. We'll go row 2 with 3 lots of row 1, take row 2. Okay, 1, 2, 3, 1. So 3 take 3, 0. 6 take 6, 0. 0, 0. Okay, this one stays the same. And if we try break this one down, okay, let's go, let's replace row 3 with 2 lots of row 1 plus row 3. 0, 0, 0. So 2 plus negative 2 is 0. All of these are going to 0. But the point that I want to make is that here we have a number. Okay, we have a number left over here. So the direction vectors of the normals are the same. All right, these have the same direction normal. They're all scalar multiples of one another. But this one's a little bit different. We're going to have a number left over here. Okay? It's not that the whole plane is a scalar multiple, it's only the direction vector of the normal on this plane that is a scalar multiple. So because the planes are not scalar multiples, only the direction vector, this means this one is hovering slightly above. Okay? It's parallel. It's parallel if, when you reduce it, there's just a number left over. This plane is parallel to the other two, which we established are coincident because they are scalar multiples of one another. Okay, so what you're doing then with these ones is you can work through and discussing the relationships that are popping up there. So I'll leave that. We've got a couple more to do together. Let's go on to question 9 then and solve this one together. This is a good one. We've got the row operations involved, we're finding values of k and so forth. So let's get into this one. Okay, consider the system of equations. I'm just going to state it straight away in row echelon form. We have x and z, so that means y is 0 equals 0. And we have 2, 1, and minus 1 and k. Okay. Now, remember, excuse me, I've got a sneeze coming. Remember, if we're trying to put it into row echelon form, then we sort of want a 0 here, a 0 here, and a 0 here. Now, we've already got a 0 there. So one thing you can do with these is it doesn't matter what order the rows occur in. Like, this is how it's given to us, but we can straight away swap row 3 and row 2. So I'm going to do that. I better state that I'm doing it. So if we go like this, I think swap row 3 with row 2. 2, 1, minus 1. Okay, goes in the second row. 1, 0, 1, 0. I'm actually not sure if this is going to help actually. No, it won't. Doesn't matter. Maybe let's just go on this wild goose chase because row operations, it doesn't matter how you do it, eventually you will get to the solution. So I've swapped these around thinking, oh yeah, we want a 0 there, but that 0 is going to disappear straight away. Okay, so let's try and break it down. We want to have a 0 here, a 0 here. Maybe even, let's get a 0 there because then we'll be able to subtract it. So let's get a 0 there. Yep. Although that becomes k take 3. Let's do it. So let's replace row 2 with row 1 take row 2. Okay? If I go, I'm going to replace row 2 with this row, take away this row, 1 take away 1, that's going to give me a 0 there. We'll have now 1 take away 2, 1 take away 1, minus 2 plus 1, minus 1, and then we'll have 3 take away k. 1, 0, 1, 0. All right, okay, we can see the solution now, hopefully. Now let's replace row 2 with row 3 plus row 2. All right, So we've got 1, 1, minus 2, 3. Now if I'm replacing row 2 with 1 plus minus 1, we're going to have 0, 0 plus 0, 0, 1 plus minus 1, 0, and 0 plus 3 take k. We'll just have 3 take k, and then this row stays the same, 1, 0, 1, 0. All right, we've almost got it how they want it. We just need to adjust this one a bit. And so, I shouldn't have done this at the start. Let's just swap it again. So we'll go swap row 3 and row 2. State what we've got, 1, 1, minus 2, 3, 1, 0, 1, 0, and 0, 0, 0, 3 take k. Okay, we've got the bottom row right. Okay, the bottom row is exactly, is almost exactly what they want. They've written as k take 3, we've got 3 take k. We can fix that quite easily. So I did say before as well, we can do 2 row operations at the same time if you want to. So let's do that now because we fixed row 3. So we're going to do 2 row operations here. Let's replace row 3 with negative row 3. Okay, we're just multiplying row 3 by minus 1. That's going to give us the k take away 3. At the same time, let's replace row 2 with row 1 take row 2. Okay, so we're doing 2 things. 1, 1, minus 2, 3. So the top row stays the same. Now, if I'm doing row 1 take row 2, so I have 1 take 0. Sorry, 1 take 1, 0, 1 take 0, 1. And I have minus 2 take 1, minus 3. And then I have 3 take 0, 3. And then this last row we've multiplied by minus 1, which gives us k take 3 instead. Minus 1 and 3. Okay, one more thing to do. Multiply row 2 by minus 1. Okay, I suppose it's sort of good we went on the wild goose chase because what I'm able to demonstrate to you is that although we did it in an elongated way, you're still able to arrive at the solution. Okay, so that's what it wants us to show that the system can be reduced to. We've successfully reduced it there, although we probably did a few extra steps along the way. All right, state the value of k for which the 3 planes meet along a common line. Okay, so flick back a sec, and let's have a look at the row echelon form. So they meet along a line in the 3 planes for which the 3 planes meet along a common line. So when there's one common line that unites them, that's number 1, 2, and 7. Now we know it's not 1 because they're not coincident with one another. We know it's not 2 because we don't have any planes that are coincident with one another. So it's going to be 7. And they want us to say, well, what value of k makes that true? So that's going to be true when this term is 0. Okay? It's only going to satisfy that row echelon form when k take 3 equals 0, which means k equals 3. If the value of k is 3, then they will meet along a line as described in 7. Okay, determine the equation of the line in this circumstance. All right, let's go ahead and do that. So if k is 3, this one's going to be 0, which means we have the bottom row zeros, so we're only considering the first part of the equation. We'll have minus y plus 3z equals minus 3. Yeah, from there, and we can go let z equal t and solve through. So we'll have minus y is minus 3 take 3t, y is 3 plus 3t, and we can solve for x as well. X equals 3 take y 2z equals minus 5t. Alright, so we solve for the line over which they meet. Here's the z value, here's the y value, here's the x value by solving this system of equations when k is 3. Okay, so that's this is all part A. So we've done part A, part 1, 2 and 3. Okay, we're going to investigate a new part. For k equals 6, the 3 planes and their parallel lines of intersection can be represented by the following diagram. Okay, determine an equation of line 1, the intersection of planes P1 and P2. Alright, so plane 1 and plane 2. So we've got 3 planes in space and they've given you a diagram alongside, but they want you to find just one particular solution. So that means we're only going to focus on the equations of plane 1 and plane 2. Okay, so we can solve this equation quite easily actually. We go let z equal, we'll use a new parameter for this question because we have already used t, so we'll use lambda. So if z is lambda, then I'm going to have x plus lambda equals 0. X is equal to negative lambda. Okay, that's from my bottom row here, and then we'll use the top row to solve for y. At the top row we'll have minus lambda plus y, take 2 lambda equals 3, and so we can rearrange this to get 3 plus 3 lambda for y. So plane 1 and plane 2 meet along this line. Z is lambda, x is minus lambda, y is 3 plus 3 lambda. Okay, so that's B part 1. Points A, B and C lie in the plane x equals 1. And the point D lies in the plane x equals 0. Find the coordinates of A and D. Okay, so that's quite tricky. So, however, we have found, okay, let's focus on point D first. Point D lies on this line. Alright, we can see that from the diagram. Point D lies on the intersection of plane 1 and plane 2. Alright, now we're told point D lies in the plane x is 0. So that means the x coordinate of point D is 0. So if you think of D, it's got 0, it's got some y value and some z value. Now, if x is 0, it means the value of lambda is 0. Okay, so if lambda is 0, then it means the z value is 0 and the y value is 3. So that means D is 0, 3, 0. Okay, so that's sort of one mark, but it requires a bit of reasoning to establish that that's true. Okay, so that's the coordinates of D. And then the coordinates of A lies on the same plane, on the same line, but A has an x value of 1. Alright, so if the x value is 1, if x is 1, that means lambda equals minus 1, which means the z value is minus 1, and so the y value is going to be 3, take 3, 0. Alright, so we're just solving there for those coordinates of A and D. So these questions, okay, these are very common, like every exam for the past 15 years has had a 3x3 system of equations for you to solve with some unknown so that you have multiple solutions, and then they get you to investigate a particular case. They're very common. So we've gone over one of them there. If you just flip the page, we've got question 10 there on page 58. This is similar. It wants you to find the solutions. And then we've got a different question again on page 59 that is using these same techniques. Okay, so you've got a system. Sometimes they'll give it to you in reduced row echelon form. Sometimes you will have to perform the operations. When you're performing the row operations, you have to specify what you're doing in order to get the marks. Okay, so you must communicate what have you done to manipulate the system of equations. So we've gone through a fair bit today. I won't go through these examples. I'll leave them for you to go with. But if we have a look at exercise 6K in our textbook, it starts off with just talking about how do two planes intersect. Okay, so there's only 3 solutions. They're either coincident, parallel, or they intersect somewhere. So 2 aren't too bad. And you can see, for instance, if we're on 6K there, question 2, we're going to check out different solutions. We've got values of K that are going to adjust the height of one of the planes to make them either coincident or parallel. All right. So in this exercise, it's up to you where you dedicate your efforts. Okay. So I'll just talk about a few things that we've got that we've got. So we didn't go through all of the ones on page 56, talking about all the relationships and how they occur. I do recommend doing that at some point. All right. Nonetheless, the relationships will pop up throughout this textbook exercise. So definitely what you should do is start with question probably 1C. All right, so let's make a list of order I recommend. So if we're on 6K, I recommend just starting with 1C, so there's some 1s to do in there. Question 2, and then question 4. So definitely that's what I'd like you to have a question for. 5 and 6 are good, although yeah, 5, question 4. And then 5, 6, 7, they're starting to look more like the exam questions. The reason I select these 3 first is because it's just involving the row operations and identification. Okay, 5, 6, 7, they get a little bit more tricky because they're getting you to analyse different values of K or M such that a statement about it is true. Okay, nonetheless, we have gone through the skills for all of them. I don't want you to get bogged down on things like 1A or 1B or question 3. So, what do you reckon? Looks okay or a bit overwhelmed or? Stop that.